Hello everyone. Today we're going to look at single area OSPF. Now there are multi-area OSPF, but it's not covered within the scope of this particular subject. These are the sections and objectives that we will be covering within the course or within the topic. So first, let us look at OSPF characteristics. Previously, we have learned about two examples of dynamic routing, which is RIP and EIGRP. So how does OSPF characteristics differ from these two? The first thing is that OSPF is a link state routing algorithm. Okay, EIGRP is like a mesh, but it is based on distance vector. RIP is distance vector. OSPF is actually a link state routing protocol. And here it shows you how it progressed from 1988 until the version that we have now, which is version 2 for the normal usage, and we have the version 3 where it can be applied for IP version 6. Now, features of OSPF, version 2 supports MD5 and SHA authentication. Version 3 uses IPsec for authentication. Supporting a hierarchical design system through the use of areas, single area, multiple area, and routing changes trigger routing updates. It doesn't do every 30 seconds an update. OSPF uses the Dijkstra shortest path first, or SPF algorithm, to choose the best path. The AD for OSPF is 110. Okay, and as you know, AD is used to determine what route gets installed in the routing table when the route is learned from multiple sources. The lowest AD is the one added to the routing table. Now, within OSPF, there are a few things or databases and tables that you need to know. First, we have a neighbor table, okay, and it uses the adjacency database. Neighbor table is a list of all neighboring routers to which a router has established bidirectional communication. It is unique for each router because every router would have different neighbors. And to view this table, you type the command show IP OSPF neighbor. Then we have the topology table. Topology table lists information about all other routers. Represents the network topology, so all the routers within that network topology. It contains the same link state database as all other routers in the same area. To view the topology table, you show IP OSPF database. Then you have the routing table. You know about the routing table. It lists routes generated when the shortest path first algorithm is run on the link state database. Unique to each router and contains information on how and where to send packets destined for remote networks. View using show IP route command. OSPF has different packet types. There is a hello packet. I'll give you a second to guess what it does. I'm sure you got it. Then we have the database description, the link state request, the link state update, and the link state acknowledgement. These are the types of packets OSPF has. So this is the basic link state operation that happens. First, when this router is switched on, it will send hello packets to establish adjacent neighbors. Okay, so it will send hello packet to all the neighbors that is directly connected to it. Then the neighbors will use the link state advertisements or LSAs to flood the area with cost and state of links of this particular router. So now he talks to his neighbor and then his neighbors disseminate the information. After the routers get all the LSAs, each router builds a topology table. Okay, and then each router runs a shortest path first algorithm resulting in the SPF tree. And using this SPF tree, each router builds a routing table that includes the path to get to the distant network and the cost to get there. So, for example, here, to go to 10.11.0.0, you have to go from R1 to R3 to R4 to R5. Now, if this were RIP and it follows hop count, this is not a good path. But because the cost is the lowest, you would find that even though it has many more hops, it will choose this one to put in the routing table. So this is the difference between a single area OSPF and a multi-area OSPF. Single area OSPF is where all routers contained in one area. It's called the backbone area and known as Area 0. It's used in smaller networks with fewer routers. Multi-area OSPF is designed using hierarchical scheme. All routers connect to Area 0, and you can look at Area 0 as the middleman, the one in between connecting these two different areas. Multi-area OSPF are most commonly seen with numerous areas around Area 0. Routers that connect Area 0 to another area is known as the Area Border Router, or ABR. This is used in large networks. Multiple areas reduce processing and memory overhead. A failure in one area does not affect the other areas. So it's logical that when you have a big network, you want to put them into areas so that if there is something going down or there is a problem, it doesn't affect all the networks within the topology. OSPF adds its own layer 3 header after the IP layer 3 header. Okay, so you see here, this is the data link frame header, this is the IP packet header, and then OSPF packet header, and then OSPF packet type and specific database. So the IP header contains the OSPF multicast address and the protocol field of 89, which indicates it is an OSPF packet. Do you remember the protocol field for EIGRP? OSPF packet header identifies the type of OSPF packet, the router ID, and the area ID. Okay, is it area 1? Is it area 0? OSPF packet type contains the specific OSPF packet type information. So is it a hello packet? Is it a data description packet? Is it a link state request? And so on and so on. So OSPF version 3 has similar packets. Remember, OSPF version 3 can support IP version 6. So it has the hello packet. Hello packet is used to discover neighbors and build adjacencies between them. Database description, or DBD, it is used to check for database synchronization between routers, meaning that if you have something different or you have added a new route, then it triggers an update to all your neighbors. Link state requests specific link state records from router to router. Link state update sends specifically requested link state records, and link state acknowledgement acknowledges the other packet types. So when somebody sends a request, there will be an update. Hello packets are used to discover neighbors, establish neighbor adjacencies, advertise parameters both routers must agree upon in order to become neighbors. So they must have certain things that they agree upon, like dead interval, before they can actually talk to each other. And then hello packets is also used to elect designated router and a backup designated router on multi-access networks like Ethernet and frame relay. This doesn't happen in serial point-to-point links. So if you look here, this is the basic hello packet if you want. So version is whatever version of the OSPF. Type here is 1 because type 1 is hello. Okay, if DBD is 2, LSR is 3, and so on. You have router ID and area ID. What area it is, what is the router ID. This router ID is similar to the one in EIGRP. Area ID, is it area 0 or area 1? And we have hello interval. Hello interval tells you how often a router sends hello packets. Why do you need hello packets? After you establish your neighbor, you need to know that your neighbor is alive. If it's very quiet, that means something is wrong with your neighbor. Router priority, the default is 1. Once you configure, everybody gets a default of 1. But you can change this using anywhere between 0 to 255, with the higher number influencing the DR-BDR election process. As we go on and see how DR and BDR works, there is an election, and then they will use this router priority. I will explain this later in more detail. Then we have dead interval. Dead interval is how long a router waits to hear from a neighbor router before declaring the router is out of service. Okay, how long do you wait? Because sometimes if you switch off a router and then you switch it back on, there is a time when they are like, down. So how long does your neighbor router wait for you before chucking you out of the neighbor list? DR and BDR fields contain the router ID for the DR and the BDR. List of neighbors is the router ID for all adjacent neighboring routers. Hello and dead intervals must be the same interval setting on neighboring routers on the same link. These are some of the things that they have to discuss and agree upon. Hello and dead intervals. It is transmitted to multicast address 224.0.0.5 in IP version 4 and FFO2::5 in IP version 6. Remember, multicast. Hello packet is sent every 10 seconds by default on multi-access networks like Ethernet and point-to-point links. Sent every 30 seconds by default on non-broadcast multiple access networks or NBMA like frame relay. Dead intervals by default are 4 times the hello interval. If the dead interval expires before the router receives a hello packet, OSPF removes the neighbor from its link state database. The router then floods the link state database with info about the down neighbor. So what is important here? You have hello intervals and you have dead intervals. Dead intervals is 4 times the hello interval. Link state updates or LSU contains one or more link state advertisements. LSAs contain route information for destination networks. Routers initially send type 2 DBD packets. An abbreviated list of the sending router's LSPD, link state database, receiving routers check against their own LSPD. Type 3 LSR is used by the receiving router to request more information about an entry in the database description. Type 4 link state update is used to reply to the link state request packet. OSPF have different operational states. It progresses through several states while attempting to reach convergence. And as you know, convergence is when all of the routers within the topology have all the information about all their neighbors. Down state is when no hello packet is received, so router sends hello packet. Init state is, or initial state, hello packets are received that contain the sending router's router ID. Two-way state is used to elect DR and BDR on an Ethernet link. Xstart state negotiate master-slave relationship and DBD packet sequence number. The master initiates the DBD packet exchange. So this is part of the synchronizing of OSPF databases across the topology. Exchange is when routers exchange DBD packets. If additional router information is required, then transition to the loading state, otherwise transition to full state. So here, if you are at this state, right, if you need more information, you go to the loading state. If you don't need any more information, you have everything you need, you go to the full state. Okay? In loading state, LSRs and LSUs, requests and updates, are used to gain additional routing information. Routes are processed using the SPF algorithm and then they transition to full state. In a full state, routers have converged databases. So it starts with nothing. I don't know anything. I just started. So I need to say hello. And then I will just get information from my neighbors, who they are, what they know. And then if I need to know more, I will ask them and then update. And then when I know everything and my neighbors also know everything, we are all in the full state. How do they establish neighbor adjacencies? Without a pre-configured router ID or loopback address, router 1 has a router ID of 172.16.5.1 and router 2 has the router ID of 172.16.5.2. So look at this topology. This is the topology. They have one, but they haven't configured the router ID. So it will take the highest number of IP address. But in this case, there is only one IP address, so they will use that IP address as the router ID. So first we start with the down state, and then it goes to the init state where it says, hello, my router ID is this. Is there anyone else in this link? And then it sends multicast to this address. Router 2 will reply, hello, my router ID is this, and here is my neighbor list, meaning that all my neighbors that I know. I'm telling you right now. So it will send unicast to R1. Now R1, now that it has received the neighbor list, it will upgrade its neighbor list. So we are now in a two-way state. Then the election of DR and BDR will happen. So R1 has a default priority of 1 and the second highest router ID. It will be the BDR on this link. R2 has a default priority of 1 and the highest router ID. It will be the DR. So here a basic voting has been done in the sense that because they have the same priority, the higher IP address will become the designated router, the DR. The second highest will become the backup designated router. Of course, in this particular topology, which is like two routers, you might be thinking, why do we need to do that? But that is the process, okay? As the topology becomes bigger, of course, there will be more information for you to get to vote for DR and BDR. So why have a DR-BDR election? This is done to reduce the number of link state advertisements sent. The DR designated router is the only router used to send LSAs for the shared network. Okay? And it reduces the number of adjacencies over multi-access network like Ethernet. So the purpose of a DR is that he is like the master distributor. He will do all the distribution work. And then BDR is a backup. If DR goes down for whatever reasons, then BDR will become the DR. Okay? So not everyone is sending to everyone, and then the network will be full of LSAs. So rather than do that, one entity which is elected as DR is the one that will distribute these LSAs. Synchronizing OSPF database. After the two-way state that we saw just now, routers need to synchronize their databases and use the other 4 types of OSPF packets to exchange information. Both routers are in the XStart state, and because R2 has the highest router ID, it will send the database description packet to R1. In this next step, right, R2 sends its summary of its own link state database to R1. R1 acknowledges that, and he also sends his summary of his link state database to R2, and R2 acknowledges that. After the exchange state, we move to the loading state. While R1 is loading information from the database, he needed more information, so he sends a link state request to R2. I need more information on the 172.16.6.0 network. And then R2 will reply with the link state update. Here is the entry for that particular network that you want, and then he acknowledges the update. Thanks for the information. The moral of the story is, router is very polite. That is the end of the OSPF characteristics. What I want you to do is visit NetAcad and go through the content in there. There is a video there that is very good for you to look at. I won't put it here, but make time to go and look at that video. Okay? So I'll see you in the next lesson. Goodbye.